Hello, everybody. Good morning, or I should say good middle of the night to our friend in Australia who joins. I'm always proud of you, Andrew, for getting up in the middle of the night and joining us on our meetings and webinars. Thank you for being here with us. The time here in southern Wisconsin is 11:01 a.m. The temperature is 30 degrees Fahrenheit. That is about -1 for you Celsius users. We're having a very cool March. It's sort of payback for the very warm February that we had, but more spring-like weather is just around the corner and we are ready. So thank you for joining us today. We're going to be talking about getting a made-to-order filament that you can use just for you to 3D print your very own special materials. So we're going to talk through the process, how that works, what it looks like, and what the possibilities are with that. Let's take a look at the agenda today. A lot of what I just said, we're going to tell you the basics of the 3D printing filaments, that materials that we make already, so you understand the base of where these custom materials come in, what that process looks like, the ingredients that are involved, different types of projects that we can get involved with you. What are those costs? We'll tell you that right up front. And then how to get started with your own made-to-order filament. We do have a time for Q&A at the end of the webinar, but ask your questions as we go in the chat. If we're able, we'll answer them in time as we go along. Otherwise, we'll save those up for the end of the webinar and answer those all at once. By way of introduction, I'm Tricia Cease. I'm the president here of the Virtual Foundry. Presenting with me today is Brad Woods, a founder. He's our science guy. He invented the filament product that we make and sell. He's our CEO. Brad, give us a hello.
Hi, everybody.
Brad is remote today, so you will not be seeing him, but you'll be hearing him quite a bit as we go through the webinar. And with us, as always, as well, is Austin. He's a print tech, customer support. If you've written into the Virtual Foundry, it's quite likely that you've received a response from Austin. He knows the most about printing with our materials. Austin is in the background today helping us with resources. He'll be throwing some links into the chat as we go through to help round out the information that we're providing for you today. The webinar is being recorded and we'll post it to our YouTube channel after the session today. Sometimes it takes a couple days. We'll let you know when that's ready too via email. So if you miss anything, if you need to leave early, don't worry. The whole video will be captured and posted later. So let's get right into it. We're going to first talk about the basics of filament, FFF metal with the Virtual Foundry's 3D printing filaments. So our filament materials are made in generally the same way. We're going to start with a loading material of metal, glass, or ceramic, and we put as much of that as we can into a PLA-based binder. Because the powders are held together with PLA, they print just like PLA. So if you're already 3D printing PLA, the switch to these metal, glass, and ceramic filaments will be pretty easy. From there, the prints are debound to get that plastic binder out of there. And then they are sintered. Those those loading particles that are in the filament are fused together through that sintering process. Most of our stock filament materials complete the debind and sinter process in open atmosphere, meaning no gas or vacuum is needed. There are two current exceptions to that, and they are aluminum and titanium, which both require specialized environments. Now, once sintered, you can do anything to that final part that you would do to any other piece of metal, glass, or ceramic, welding, brazing, machining, any of those processes. Now, the parts are microscopically porous, which is a property of metal powder sintering. So that's a pretty normal piece of the process here. The images are showing you the steps from start to finish. We've got the filament line that's shaped and works just like regular PLA. You're printing in a standard FFF FDM style 3D printer. And then you're doing that debind and sinter process in a regular tabletop kiln, a pottery kiln, or the kiln can be as fancy as you want it to be. And then finally, you're doing any kind of polishing or post-processing to that piece that you would normally do. So, because all of our filament materials are made in the same way, that means that we can put nearly any solid into the process to create a made-to-order filament. Well, the first big question is, does your desired material come in powder form? So sometimes we get requests for materials. We go on the hunt to find that in a powder form to fit into our process, and we just can't find it, or it's prohibitively expensive to get it in a small quantity that we need. So that's going to be the first question. Now, this is what we're looking for from the powder. Particle size of -325 mesh, which is the majority of particles at 45 micron, the rest filling in smaller, spheroid but in shape. And we're looking for that optimum balance between minimal surface area and maximum apparent density. And as far as the volume of materials, we're looking for typically 1 to 3 kilograms, but if we look at the volume rather than the weight, that's going to equal about 2 liters of powder. Brad, talk to us about this particle size. I know that you worked with particles outside of these sweet spots of shape and size. So talk to us about some of the limitations there and how far outside those parameters we can go.
Sure. As we're adding binder, so each of the particles needs to be coated with the thermopolymer binder to make the filament strong enough to handle and not be brittle. And this is why we mentioned the minimal surface area. And what we found is that around 325 mesh or around 45 micron, we nearly always succeed. To a filament is proportionate to the apparent density of the bulk material.
So Brad, you cut out just a little bit. Could you restart that sentence, please?
Okay. Was that the apparent density part?
Yes.
Okay. So apparent density is essentially a measurement of how many particles of solid mass you can fit into a given area. And because of that, the higher the apparent density of the powders that you're working with, the higher we're able to load it as we go to make it into filament. So this is a pretty key property of the whole process. And the higher we're able to load it, the easier it becomes to sinter on the back end and the less shrinkage you have during the densification process.
So that's the first ingredient in your final filament product is the loading material. The second ingredient is our proprietary binder. We're always going to supply that piece, and it will always be the same as what we use with all of our stock materials. Now, if that loading material is something that you have hanging around and can send to us, that's great. We'll turn your proprietary or specialized powdered material into 3D printing filament. If that's not something that you have, then we'll go on the hunt for a supplier for that.
Yeah, and as metal 3D printing has expanded, and including the systems that use powder beds and lasers, essentially those are the same materials. And as this technology has expanded, the availability of materials has expanded dramatically. So we can get things now that we couldn't get even 6 months ago. So this is a pretty dynamic market.
Yes, that's a great point. It is getting easier and easier to find these materials in powder form. Now, there are some materials that will not work in the process. Those include zinc, toxic materials, highly active materials, chemically unstable compounds, strong acids or bases. Now, most of these look pretty obvious, like the reason is obvious why we are not able to work with those, but that zinc one might be a question. The chemistry of zinc messes with the chemistry of PLA. So our current binder can't be used with zinc. Unfortunately, that eliminates all versions of brass. Now, it isn't a permanent elimination. Keep your eye on us. Brass has become a bit of a personal issue. So I'm sure that Brad will get that figured out in the future. For now, we're not able to work with anything that has zinc in it.
Right. And another point is example of toxic materials. So like we wouldn't make a uranium 3D printing filament, but we have done simulants so that people can do their experiments on well, on radioactive 3D printing materials. So we'll just come up with something that simulates the final product and is a good analog for it.
So the list of materials that we cannot work with is pretty short, actually. The list, so that leaves everything else pretty much open. We're going to work with most any sinterable material. So let's take a look at how the process works. You'll contact us in some way via email, contact form, phone call, however, to talk through a custom material that you would like to have made. We'll prepare a project plan for you. We'll take a look at what that project plan looks like on a future slide. But we'll prepare a project plan for you, and that will list the full process, all the pricing, all the terms and conditions, most of which we'll talk through today. Once that is accepted, you'll send in your payment. We'll get the raw material in-house here. There may be a material evaluation step, and we'll explain that more as we go. Then we'll get into manufacturing. We'll actually convert that powder into FFF 3D printing filament. We'll do some test printing here in-house to make sure that we've achieved the goal of 3D printable material. We won't be doing any sintering trials on it though, and then we'll ship that final filament to you. Now, the weight of filament line that you receive will be just under the weight of powder that we receive. There's a small amount of waste in the manufacturing process, and then we're also doing that test printing. We're experts at getting materials into an FFF 3D printable format, and that's really our focus. So we will print with your made-to-order filament before we send it to you to make sure that it can be printed. We're not doing any of those sintering trials. And since your made-to-order filament will be made with our standard binder, we expect the debind process to be the same as our other materials. So taking a look at that project plan that I just mentioned, you're seeing a little snippet of it here on the screen. The project plan is going to lay out the goal, the process, just what we talked about, but in more detail, the pricing, terms and conditions, and then it has an area for you to sign with project acceptance. The project plan serves as your quote and includes these different sections that spell out the whole process. We can provide a standard quote document to you as well. Some of the materials that we have already made include molybdenum, molybdenum with carbon fiber, bismuth doped positive, bismuth doped negative, basalt moon dust simulant, barium titanate, titanium grade 2, magnesium 4140 steel, and a few others that we are not allowed to talk about. Some of the specific materials that you listed in your webinar registration were an aluminum bronze combo. Brad, and I'll ask you to talk about these a little bit. Aluminum bronze combo, ceramics, a bronze glass combo, a brass bronze combo, which we just learned we won't be able to do. And then rare earth metals to make twisted magnet shapes. Brad, talk about the possibilities with those materials that people specifically called out.
Sure. The rare earth metals is a really interesting one. We're getting a lot of expansion in what would you call it? Electromagnetism, things like that. So people are realizing that you can build ferrous cores with very unique shapes to them, and this is becoming a really powerful tool in green energy and uh, so new motors, more efficient motors, things that we could never do before. Another interesting one is bismuth, the one that we have listed here, and it wouldn't need to be bismuth. It can be any semiconductor. But in this example, they the customer used it to 3D print semiconductors. So they actually 3D printed Peltier devices, which are a solid state thermoelectric device, a method of extracting electricity from heat in a very, very robust way. There's no moving parts or anything like that. You just set it up and they'll run for years. Now, when you get into the different alloys, like talking about, for example, like a copper aluminum or something like that, there's a couple different ways to approach it. You can either pre-alloy the material, so you wind up with essentially melting those two materials together and then making it into a powder. You can also do the alloying at the time of sintering. So you're essentially just blending copper powder and, for example, aluminum powder. And aluminum, as we mentioned earlier, has its own specific challenges, and they're all related to the oxide layer that coats each of the particles. So there's lots of interesting options, and we'll slowly overcome this. And I think that we will get to a simple method of processing aluminum in an open atmosphere, but we have a ways to go on that. But when we're talking about the different alloys, the first question is whether it's a pre-alloy or a post-alloy. Do we start with a blend of the metals in the powder form, or do we start with two different powders? And there's all kinds of interesting things that can be done in this direction.
One of the combos that was mentioned was a bronze glass. Tell us about possibilities with that.
Yeah, I've actually done some experiments with sort of like spray coating bronze onto Pyrex or borosilicate, and they have coincidentally almost the same coefficient of expansion. So yeah, this would be a really, really interesting experiment that someone is going to need to do.
And then I think it was our friend Matt Person who mentioned ceramics. So I know that you've made different ceramic materials before. What are the limitations there, if there are any?
The limitations would be the same as you would find in any other application. And typically, the limiting factor becomes a compatible coefficient of expansion. If you have two materials that expand and contract at different rates at different temperatures, it'll simply break. It'll crack. It's like when you heat glass too quickly in your kitchen or something and the glass fractures. It's the same problem. So yeah, finding compatible materials isn't terribly difficult. On the glass side of things, there is an art technique called fusing and slumping. There is there's a company called Bullseye Glass. They make dozens of different varieties of glass with different coefficients of expansion. So you can pretty much just pick off of a menu, find something that it will be compatible with whatever material you're working with. Again, uh, lots of interesting experiments here that need to be done.
So speaking of these different kinds of materials, the question came in, zinc will not work. But what about a zinc oxide, which is more inert at room temperature?
That's a great point. I hadn't thought of that. Yeah, in fact, I wonder if we could even reduce the oxide off of the zinc. We'll be trying that.
Okay, that was a great question. Thank you for asking
Yeah,
that.
good one.
It's always fun. It's always fun to stump Brad and tell him something that he hasn't thought about before. So good job on that one. We don't get to do that very often. Now, also listed in the signups was a different powder PLA ratio, and we'll talk about that more on the next slide. Which is where we get into development projects. So we've been so far talking about made-to-order filaments. Now we're talking about development projects, which are a little bit different. Made-to-order filaments, we're generally talking about one loading material into our standard binder. We're manufacturing it in the same way that all of our other materials are manufactured. It presents a fairly straightforward process. When we're talking about development projects, that's a little bit different. So you saw molybdenum with carbon fiber on the previous slide. So that's one example that's a little bit different from a standard made-to-order filament. So when a request falls outside of that category, it's in this development category. Material combinations fall in this category, although it's dependent on the materials. The development project in that case may not be priced too much differently than a standard custom run. We talked about how material combinations would work, what considerations need to be factored in where sintering is concerned. As far as manufacturing the filament, combining materials is a fairly straightforward process. It's those heat processes on the back end that really are going to affect the materials that you're choosing to combine in the process. So maybe you want an additive to one of our stock materials like graphene added to copper, for example. Or you want an additive added to your requested powder, like that molybdenum with carbon fiber. Another example of a development project is a different level of base material loading. So our typical loading percentage by volume is 50 to 60%. So as we've talked about earlier, we're always seeking the optimum balance between high material loading and printability. And that volume range of 50 to 60% is really where that lands. Sometimes we get requests for a lower loading, and that's another example of a development project. So all development projects would still involve a base loading material into our standard binder. Brad, talk to us a little bit about these requests for alternate volume loading or alternate mass loading than what we typically work with.
Yeah, it seems intuitive that it would be easier to manufacture something with, say, 5% bronze than it would at 80% bronze. But in practice, that's not true. It's actually more difficult for us to manufacture very light loadings of the additive material. We can do it. We just need to change the way that we manufacture it. And it can get a little bit complicated. So typically higher loadings are easier for us.
So a couple of projects that we won't be taking on at this point are alternate binders and non-sinterable materials like coffee grounds. So we will stay away from those projects for now. So let's get into the costs of these things. Now, talking about the made-to-order filament, that first category of project that we talked about, the manufacturing fee is $5,000. The powder cost, if you send it to us, obviously that's zero, you're supplying that. And then the price, if we source it from a supplier out there, is material dependent. We would get a quote for that and forward that on to you. Excuse me. The cost of the binder is included in the project. Now, base material evaluation could come into play if your material is outside of our typical scope. So if you want a nickel-based filament, for example, the evaluation fee likely won't apply. Where it does apply if you want us to use a powder with morphology that's outside what we described, that -325 mesh spheroid. Or maybe the powder is very special to you and your organization, and we haven't seen anything like it before. That's a case where an evaluation fee may apply. Brad has some standard bench tests he can do to determine feasibility for our manufacturing process. So that would be a separate upfront fee. If the powder does not meet the requirements for our manufacturing process, that's where the project stops. So then we would not get into any more fees for that. But if it does meet the standards for our manufacturing process, we'll go forward with that manufacturing project then. Shipping of the final material is included. Shipping of the powder to us and shipping of the final filament material is included as long as all of these addresses are within the USA. If we have to import the powder, we can't find a US supplier, for example, those importing costs will be a part of the project cost for you. Cost for development projects, that's where we talked about different material loading percentages, additives to the 3D printing filament. Those are going to be on a case-by-case basis. So there we'll take a look at the project, what your goals are, the results that you're looking to achieve, and we'll put together a plan. We would still use that project plan, so you would see everything that goes into it, all the cost breakdowns and things like that. So those development projects, those more special projects would be priced on a case-by-case basis. Now, the resulting new product may be something that's proprietary to you, and that's awesome. If it's not, and it's something that we'd like to move forward into commercialization, we can work with you to come up with a profit sharing plan so you recoup some of those development costs. Now, you will see this situation in our current catalog with products that have alternate names and include another company's logo on the spool labeling. So Rapid 3D Shield Tungsten Filament is one of those, and that was created through a joint venture between the Virtual Foundry and Vulcan Global Manufacturing Solutions. They're a lead products manufacturer who was looking for a non-toxic 3D printable radiation shielding. So they came to the Virtual Foundry to commission the tungsten product that we now produce. So that's one situation. And the second is the basalt moon dust filament that we just released. And that was created through a partnership with Astroport Space Technologies. So we do welcome these types of partnerships. If you have something special you'd like to see in filament form and then go into commercialization with it, we're certainly open to talking with you about that. More on the cost side of things, a few terms and conditions. The quotes and the project plans are valid for 90 days. Shipping costs and import duties, we talked about that. Raw powder, we'll always try to source the powder from the USA first. That's one of our general principles. Our current material stock all comes from the US. If we do need to import that powder in, you'll need to pay for those costs. And it's going to be a 2 to 4 week lead time from powder receipt to shipping of the final product. Keep in mind that sometimes once we locate a supplier, they have a lead time as well. So our clock starts when we get the powder in-house here. About the payment, that's required before work begins. Credit card, wire transfer, ACH transfers, the normal methods of payment. And the payment is rendered for work performed in good faith, regardless of the outcome. So we've got lots of years of experience, lots of making 3D printing filaments. We've worked with a lot of different materials. Most of the time it works great. Once in a while it doesn't, as we've been talking about with the zinc. So you will get the Virtual Foundry's very best effort in producing these materials. And that's really what the fee is for, that experience, that knowledge that goes into being able to take your special material and put it into a 3D printing format. So how do you get started in this process? We have a document that outlines everything. I will send this to you in the follow-up email. It will also be linked in the YouTube description once the video is posted to YouTube. But we've got a document, it's on the homepage of our website towards the bottom, that outlines the whole process. It talks about everything that we did here today, the desired powder size distribution and shape, what the process looks like, the costs, all of that is outlined in that document. We also added a custom filament product to our shop. So you can go straight to our online store and find a custom filament product It will talk about the process a little bit there. It's an abbreviated version, but also gives you a link to reach out and contact us about that. I will send you a sample project plan in the follow-up email that I send you after the webinar as well. So you'll be able to see what that document looks like. And then when you're ready to get started about talking about your own material, you can write to us at info@thevirtualfoundry.com or give us a call in the US +1 608 509 7146. Well, next up is the Q&A. We had a question in the chat that we answered in line there. Thank you for that question. So I'll just give you folks a second here to ask any other questions. Okay, it looks like, oh, go ahead.
Oh, I was just going to say, I'll speak about the concept in general.
Okay.
And what we're looking to do is be able to manufacture things that have never been manufactured before. So 3D printing, it's a new method of fabrication. And I talked about the pre-alloys and the post-alloys. There's just a huge list of things that need to be experimented with. And our goal here is to enable the new manufacturing methods of new materials as we go along.
Yes, thank you for that, Brad. The custom projects are some of our favorites around here. People do pretty amazing things with these materials, and that's really fun to watch. So we did get a couple more questions in. Brad, I'll ask you, what about cross-contamination?
In our standard process, there's always a minuscule amount of cross-contamination. And we've been preparing for this because there will be medical applications that need to be absolute perfection. And I think what we'll wind up doing is there will be an additional fee for something that has as close to no cross-contamination as possible. But generally speaking, all of these materials are processed on the same equipment, and there is no way that I could ever say that there is no cross-contamination. Though we are very diligent, it's minimal.
Another question, this is about applications. Would the metals be usable for tool usage, such as hammers, pry bars, wrenches?
Yeah, there's no reason that it wouldn't. They'll be just as usable as, I try not to say, it's not exactly the same as if you were to forge a hammer, for example, because it's a product of powder metallurgy, which has some of its own implications. If you're looking for a good analog, you can do research on metal injection molding. So the properties of sorry, I saw zinc pop up on my screen. No, it gets me. But the properties of the materials, yeah, there's nothing that you really can't do. If you can do it with the metal that you're working with, you can 3D print it.
So about that zinc, why no alternative binder to PLA like PVA? So tell us about, we talked about not working with any alternate binders, always using our standard binder. Tell us about why that is.
The reason, to make sure I'm not muted, it took a really long time to perfect the binder recipe that we have now. I mean, years. And we will definitely move to other options. And PVAs, polyvinyl alcohol, is a perfect example. We'll probably do something like that for the zinc products or things that are chemically incompatible. So the only reason we're not doing it right now is we don't have a completed alternative binder recipe that's ready to go.
Okay, that looks like all the questions in the chat. So Brad, I will ask you one more very important question before we wrap up the webinar. Why do cows wear bells?
I can't imagine.
Because their horns don't work.
Nice.
Well, thank you everyone for joining us today. If you have any other questions or want to talk about your own custom material, write to us at info@thevirtualfoundry.com. We'd love to talk to you about it. Like I said, those are some of our favorite projects. We'd love to see what you're doing out there in the world with these materials. Really cool stuff. So thanks everyone for joining us. And until next time, happy printing, everybody.
Thanks.